All right, let's jump right into this explainer. We're unpacking a massive, invisible machine today, the engine driving the entire Indian climate. We often think of weather as just, well, something that happens to us day by day. But when you look at the Indian subcontinent, you're actually looking at one of the most complex, highly synchronized atmospheric engines on the entire planet. And today, we're going to break down exactly how this incredible system works. Here's the really wild part. 80% of India's annual rainfall dumps down in just a few short months. I mean, think about that for a second. An entire nation's water supply, the very thing dictating the agriculture, the economy, and daily survival for over 1 billion people, arrives in this highly condensed explosive window. We aren't talking about a steady drizzle spread across the year. It's a dramatic seasonal event that literally transforms the landscape overnight. To figure this all out, we're going to treat the climate like a giant engine. We'll start with the casing that protects it, dive into the core mechanics and gears, look at the global remote controls that hack it from afar, trace its actual life cycle, and finally, look at the output, the rainfall and the seasons. Let's get into it. Starting off with Section 1, the climate engine. Let's see how the physical geography sets the perfect stage here. The physical geography here is absolutely wild. The Himalayas basically act as a colossal physical shield. If you picture a globe, India sits right next to the freezing expanse of Central Asia and the Arctic winds, right? But because of this towering mountain range, those chilly, freezing winds are completely blocked. The topography literally cuts the subcontinent off from the harsh continental winters of the north. It's a massive climatic divide. And because of that giant mountain shield, India maintains a uniquely unified climate, which we call a tropical monsoon climate. Normally, when you travel north of the Tropic of Cancer, things get pretty temperate and extreme. But not here. In India, thanks to the Himalayas, the entire landmass falls entirely under this unified tropical monsoon banner. And the defining feature of that? The seasonal reversal of its winds. All right, moving on to Section 2, the gears of the monsoon. How does this whole flow actually reverse? So how do the winds actually flip? It all comes down to a complete, dramatic reversal of temperature and pressure. In winter, cold conditions up in North India create a high-pressure zone which pushes dry winds out from the northeast toward the ocean. But summer bakes northwestern India, creating this massive low-pressure vacuum. This thermal vacuum literally sucks in winds from the ocean, completely reversing the flow into moisture-laden southwest winds. It's a complete 180. Now, to really understand these powerful summer winds, we have to talk about the ITCZ, the Intertropical Convergence Zone. Think of this as the equator's thermal equator. It's a low-pressure belt that physically shifts north over India in July. As it shifts, the vacuum is so intense that it pulls the southeast trade winds from the southern hemisphere right across the equator. And as they cross over, they pick up immense moisture from the warm ocean currents, transforming into the massive southwest monsoon. But wait, it's not just happening on the ground. Way up in the high atmosphere, fast-moving rivers of air called jet streams are doing their own flip-flop. In the winter, you've got the westerly jet stream bringing in cyclonic disturbances all the way from the Mediterranean into northwest India. But come summer, an easterly jet stream develops instead. This new stream steers aggressive tropical depressions directly into the subcontinent, acting as the primary delivery system for those heavy monsoon rains. Which brings us to Section 3, the global puppeteers, because this local engine is actually hacked by weather anomalies thousands of miles away. Let's zoom out to the Pacific Ocean and look at the El Niño Southern Oscillation. Think of El Niño as a high-stakes tug of war that actually steals power away from our Indian climate engine. See, there's this atmospheric loop called the Walker cell. In a normal or La Nina year, the Indian Ocean branch of this cell strengthens, pumping intense, moisture-rich winds right into India. Great news for the monsoon. But during an El Niño year, the ascending branch of the Walker cell shifts toward the central Pacific. This pulls energy entirely away from India, weakening those southwest winds and causing a really poor monsoon. Closer to home, there's the Indian Ocean Dipole. You can picture this like a giant thermal seesaw right in the ocean. When the western side near Africa tips warmer than normal, that's a positive phase. It drives increased convection and fantastic precipitation over India. Super favorable. But if that seesaw flips to a negative phase, the warmer water shifts east, and it draws all that precious rain entirely away from India. And then there's this really fascinating variable called the Madden-Julian Oscillation, or MJO. Imagine an eastward-moving pulse of storms and clouds traveling along the equator every 30 to 60 days. It's essentially a traveling rainmaker. If this pulse happens to be passing right over the Indian Ocean during the monsoon season, it dramatically boosts the rainfall. For a farmer waiting to plant, whether this pulse sits over the Indian Ocean or the Pacific can literally be the difference between a bumper crop and a devastating drought. Let's get to the main event, Section 4, the monsoon life cycle and the big burst.
So how does this violent onset actually sweep across the map? Well, it starts down in the Andaman-Nicobar Islands around May 15th. By June 1st, it hits the Kerala coast with violent thunder and lightning, a phenomenon that's literally called the burst of the monsoon. From there, it just marches steadily north. It hits Mumbai and Kolkata mid-June, and by July 15th, it covers the entire sprawling landmass of India. 2 months, and the whole country is engulfed.
Now, when this system hits the southern tip of India, it executes a massive pincer movement, splitting into 2 distinct flanks. The Arabian Sea branch on the west coast is an absolute powerhouse, literally 3 times stronger than the other. It crashes into the Western Ghats and sweeps across central India. Meanwhile, the Bay of Bengal branch sweeps up the east side, strikes the coast of Myanmar, hits the Arakan Hills, and gets completely deflected back into West Bengal and the Ganga Plains, eventually merging back with the Arabian branch. But, every engine has to power down eventually. By September, that intense thermal low-pressure zone over North India starts to cool off and fade, and the whole system goes into reverse. Starting September 1st in the far northwest, in Rajasthan, the monsoon begins a systematic retreat. By mid-September, it's out of Punjab and Gujarat. Those moist southwest winds are gradually replaced by dry northeasterly trade winds as the whole massive system resets itself.
Finally, Section 5, Rainfall and Seasons. What does the output of this engine actually look like on the ground? Ultimately, it's the local topography that decides who gets life-giving rain and who gets stuck as a parched desert. Generally speaking, rain drops off the further inland you go, decreasing from east to west across the northern plains. But here's a crazy fact. The Rajasthan desert stays completely dry, even though the monsoon passes right by it. Why? Because the Arabian Sea winds blow exactly parallel to the Aravalli mountain chain. Without a mountain right there to force the air up and literally squeeze the water out, the moisture just sails right on by.
Broadly speaking, this entire subcontinent experiences 3 dominant climatic periods driven by these massive temperature and wind shifts. You've got winter from mid-November to February, marked by clear skies and those Mediterranean westerly disturbances. Then summer hits from April to June, baking the land up to 45 degrees Celsius, which, remember, sets up that crucial low-pressure vacuum. And finally, the southwest monsoon from June to September, delivering that critical 80% of the annual precipitation we talked about earlier. But if we look culturally and agriculturally, this intricate engine actually produces a beautiful plurality of seasons. Beyond the main 3, traditional Indian calendars recognize 6 distinct seasons, carefully tracking the really nuanced shifts in the weather. You move from Vasanta, or spring, into the scorching Grishma, followed by the Varsha rains, then Sharda, or autumn, Hemanta as pre-winter, and finally Shishira, the deep winter. It just goes to show how deeply tied human life is to the subtle rhythms of this atmospheric machine. And this vast system creates some incredibly localized quirks, too. While almost the entire rest of India is flooding under the summer monsoon in July, the Tamil Nadu coast down in the southeast is just sitting there, totally dry. Because it lies in the rain shadow of the western mountains and parallel to the eastern winds, it misses out entirely. Instead, Tamil Nadu has to wait all the way until the winter when the retreating northeast winds pick up moisture over the Bay of Bengal and finally deliver their rain. So when you put it all together, what we see is that these massive, globe-spanning atmospheric forces, the jet streams, the El Niños, the shifting pressure zones, are all ultimately filtered through the local physical geography of India. The mountains, the plains, the plateaus. The physical relief of the land is the final, ultimate arbiter that decides exactly where every single drop of water is going to fall. Which leaves us with a pretty vital question to ponder as we wrap up this explainer. This atmospheric engine has run like absolute clockwork for millennia, heavily relying on the delicate balance of ocean temperatures in the Pacific and Indian Oceans. But as our global oceans warm and anomalies like El Niño become more frequent and unpredictable, how will this ancient, interconnected climate engine survive the changes? Will it adapt, or will the gears start to slip? It's a question that holds the future of 1 billion people in the balance. Thanks for joining me today, and keep your eyes on the skies.